All right, welcome back to day 3 of cooking in Lattice QCD. We're going to finish up light flavor physics on the lattice today. So let's just get right to it. Today we're going to focus on non-leptonic processes. And so these are processes where, well, as I said before, there are no leptons. It's a very apropos name. The two main types of processes that we'll talk about, because these are the most relevant for lattice calculations, is neutral kaon mixing, okay? So KK bar mixing. And this shows a neutral kaon via this box diagram turning into a neutral anti-kaon. And in your previous set of exercises for the previous lecture, I actually had you work through some of this already, at least the lattice side of things. And some of the exercises that are related to what we would normally do in preparation for a lattice calculation. And of course, this process shows how a particle can turn into an antiparticle and back and forth. So it's one relevant process for understanding CP violation in a standard model. The other, at least generic process we'll talk about is k to 2 pi. And I'll generally refer to it as just k to 2 pi. What I'm showing here are processes for a neutral kaon, k naught, decaying into a two charged pions, pi plus, pi minus. There are other versions that could occur here of different types of decays, but these are the ones, this is just one example. And you can see in this case, there are lots of diagrams that can participate in this quantity. And these are just Feynman diagrams. Part of your exercises will actually be to look at the possible quark contractions you need to look at on the lattice, okay? So let's talk a little bit about kaon phenomenology, and specifically that related to CP violation, my very fancy way of writing CP violation. Now, recall that kaons have isospin 1/2, so they'll either have one up or one down quark in them, and then a strange quark or anti-quark in the other case. We generally will not worry about quark versus anti-quark. If I talk about two quarks in a meson, I mean a quark and an anti-quark, of course. And pions have isospin 1. Right? We can have two up quarks, two down quarks, or one of each. So when you have k to 2 pi decay, the 2 pion final state can either be isospin 0 or isospin 1 or 2. So we either are going to go from a isospin 1/2 state to 0 or to 2. I keep saying 1. Such processes are often referred to as delta I equals 1/2 or delta I equals 3/2. So in the case where I'm going to the isospin 0 channel of the 2 pion state, that's obviously a delta I equals 1/2 process. And then if I'm going to a 2 pi state that has isospin 2, then it's a delta I equals 3/2 process. The three most prominent processes that we'll discuss are shown here. And I'm showing the transition amplitudes for k naught goes to 2 neutral kaons, k naught goes to pi plus, pi minus, and of course, a charged kaon goes to a pi plus and a pi naught. And we can write this sort of generally in terms of these amplitudes A2 and A0. Those are going to correspond to whether or not you're looking at the isospin 0 or isospin 2 final channel. And then some phase factors, delta 0 and delta 2. These coefficients here, so 1/√3, 1/√6, square root of 2/3, those are just Clebsch-Gordon coefficients that allow us to relate the different isospin channels. If the standard model has CP violation, then these different coefficients, the A0 and the A2, are not real, right? So A star is not equal to A. And so they'll all have a real and imaginary part. Of course, the deltas are still real. Okay. And so this is what we want to try to calculate on the lattice. So how do we do that? So before we get to that, we still have a little bit of more work to do. And again, some of this will be discussed more in your pre-class assignments and work that you'll have to do. But we generally think about CP acting on K naught as giving us, I could choose any phase factor. I'll choose -1, that if I act charge parity or charge conjugation and parity on K naught, I'll get something proportional to K naught bar. And I'll choose, it's got to be a phase factor that's equal to 1, that squares to 1. I'll choose a negative sign. And the same is true for CP acting on K naught bar. And so these are not CP eigenstates, right? CP converts a particle to an antiparticle. And so we can define what ideally will be true CP eigenstates of the standard model. This is what I'll call K plus and K minus, not to be confused with the charged kaons. The superscript plus minus will correspond to the charged kaons. The subscript plus minus corresponds to the CP eigenstates. And it's a quick check that in fact this notation makes sense given this relationship. If CP is conserved, then K plus and K minus would be the physical states of our theory. But that's not what we see. Okay, what we actually see are these two states, K long and K short, or KL, KS, where L corresponds to the upper signs and S corresponds to the lower signs on the right-hand side. And this epsilon factor is something which, if 0, would indicate that CP is conserved in the standard model. And in which case, K long and K short would be CP eigenstates. And this is, you've probably heard of the tau theta puzzle from back in the day, well before my time even, where you had kaons being able to decay to either 2 or 3 pions, which violates parity if parity itself is conserved. But of course, we know parity is not conserved in the weak interactions, so that's not a big deal. K long primarily decays to the 3 pion state, we say, and that has a very long lifetime, about 5 times 10 to the negative 8 seconds. K short decays to primarily the 2 pion final state, and that has a much shorter lifetime, hence the name K long, K short. And the bulk of this difference can be summed up by the amount of phase space available. Right? There's much less phase space available with a 3-particle final state than a 2-particle final state. One big source of CP violation actually comes from the fact that the neutral kaon, the K naught and K naught bar, mix. They can oscillate back and forth between each other. And so how does that come into play? Well, let's see how all this works out. Well, there are several sources of CP violation. We often refer to direct CP violation and indirect CP violation in the standard model. And the idea is, if I jump back here, right, K long has basically a K minus and then the epsilon times K plus. Okay, so I dropped the prefactor here. And direct CP violation, I guess I could have just pointed out there. So this is K long going to 2 pi, okay, as a possibility. Because K long primarily goes to 3 pi, but it could go to 2 pi. Because, right, that would indicate CP violation. So this K long has 2 ways that it could decay to 2 pions, which in both cases violate CP conservation. First, we call it direct CP violation because we've got this CP odd state, K minus, and that should not be able to decay to a CP even state of 2 pi. So if that happens, then that's direct CP violation. Indirect CP violation comes from the K plus portion of the K long state. And that's really going to be coming through by basically oscillating from a K naught to a K naught bar. Okay, so there's sort of this indirect approach, a sort of a multi-stage process there. And both cases can correspond to CP violation in the standard model. And we parameterize these by two variables, epsilon prime and epsilon. So these are these ratios of transition element, matrix elements that I pointed out on the previous slide, where we're looking at specific isospin final states. Okay, so we're thinking K long goes to the 2 pion final state that has isospin 2, K short goes to the same, K short in both cases in the second term going to the 2 pion final state, either isospin 2 versus isospin 0, and then so forth and so forth. Epsilon is defined similarly. In one of your problems that I've given you on the pre-class assignments, I actually have you calculate what these quantities are in terms of actual experimentally measured quantities. They're called eta 0, 0 and eta plus minus. So on this slide, I just wanted to denote this parameter omega, which is defined by that second term in epsilon prime. So epsilon prime could be written as 1 over root 2 times this term minus omega. Okay, that'll be useful for both your homework as well as later slides. Because with a little bit of algebra and some simplification, you can find that omega is related to the ratio of the real parts of A2 and A0. So those are the amplitudes related to the isospin 2 or isospin 0 final state times this phase factor. So omega is going to be a complex number in general. And epsilon, not epsilon prime, but epsilon is approximately equal to this quantity here, where there's going to be some phase factor called phi epsilon times the sign of that same phase factor times this combination of quantities. M12 and delta MK are defined in the pre-class assignment. So after you watch this video, you'll see these in the homework, and I'll encourage you to come back and look at this and think about this, or make a note of this before going to the actual pre-class assignments. Plus the ratio of the imaginary to the real part of A0. And then epsilon prime is roughly equal to this. So notice there's a difference in phase factors there in the exponential piece, and then the imaginary part of A2 over A0. And all of these actually have values in the PDG that are determined. And you can sort of see the level of precision we're looking at here. Okay, so we have, for example, the magnitude of epsilon, this direct CP violating parameter, and its phase. And so notice, the phase is about 1%. This is about 0.5% precision. You can look at the real part of epsilon prime over epsilon, and epsilon prime over epsilon is approximately real. Okay, and you'll notice that it's this again combined with epsilon gives you the scale of indirect CP violation, 1.66, blah blah blah. These are a couple of phase factors that are relevant for experimental quantities. I'm just leaving them up there because I ripped this straight from the PDG. The phase of epsilon prime is given by this. And the last two things that I want to point out are delta MK. This is the neutral kaon mass difference. And so you'll see it's very small, on the order of 10 to the negative 12 MeV. It's not zero, and it needs to be non-zero in order for the K bar to oscillate to each other. Finally, we have this ratio of the absolute value of A0 over A2. And notice this is around 22. This means that the amplitude for the transition from the 1/2 isospin state to the isospin 2 state is 22 times smaller than that for the isospin 1/2 to isospin 0 transition. This is often referred to as the delta I equals 1/2 rule. And it basically states that for some reason, the delta I equals 1/2 transition is favored notably over the delta I equals 3/2 transition. Okay. Now, let's actually get to the lattice and how to calculate this. Now, for k to 2 pi, we're not going to really discuss as much of the details as we really should, because as you'll see, it's quite complex. Now, back in the 70s, it was shown by Osterwalder and Schrader that Euclidean correlation functions can always be analytically continued to Minkowski space. So in principle, and let me stress that, in principle, anything you want to calculate on the lattice in Euclidean space can be analytically continued to Minkowski space. However, that is, I don't want to say absolutely impossible, but essentially it's impossible with inexact data, right? And when we do calculations on the lattice, we're going to get results that are only approximate. Okay, there are uncertainties, there are errors in our calculation. We can't calculate exact results. And so if you don't have exact results, then this analytic continuation isn't really possible. And in fact, Magnani and Testa back in 1990 showed, well, they asked the question, what can you do if you don't do the analytic continuation? In other words, what can we actually do on the lattice? And specifically, they were looking at k to 2 pi. So here I'm writing, imagine the effective Hamiltonian, which is going to govern this transition. And notice we've got a kaon at rest decaying to 2 pions. So we're in the center of mass frame. And the problem is, and this is what they showed, that technically, at least for infinite volume, the ground state asymptotically is of this operator or of this matrix element is when all of the mesons, including both of the pions, are at rest. So you've got a kaon at rest decaying to 2 pions that are both at rest. That is kinematically impossible, right? That's unphysical because the kaon is not exactly twice the mass of the pion. And so in this case, the 2 pion state that's physical, right? And in that case, we want the energy of the pi state to be equal to the mass of the kaon. This is going to be an excited state, and extracting excited states from these spectra is difficult. Now, in a finite volume, you don't have a continuum of excited states. Okay, so this so-called no-go theorem isn't technically a no-go. Because we're in a finite volume, we have discrete energy levels. Okay, but it's difficult. Not at all impossible. In fact, there are groups that have worked on this in the last 20 years or so. But in many cases, in the early days, especially, chiral perturbation theory has been used a lot in order to try to extract the k to 2 pi matrix elements from other processes, maybe k to pi. Okay. And models, of course, are always used in these processes. But what about, how can we do this on the lattice? Okay, and one way is using the Lelouch-Lusher method. And this allows us to, I think I'm saying this on the next slide, yeah, to extract the 2 pion final state in a finite volume using scattering phase shifts. Okay, and I'm going to be giving out a bunch of references, and I'll give some references for that as well. But something that's a little bit more easy to wrap our head around here, I think, is just, let's play around with the boundary conditions. This is something that was done initially by the RBC collaboration and then by both the joint RBC UK-QCD collaboration. And if you start changing the boundary conditions of our quarks, then you're going to start changing the restrictions on the momentum. So with ordinary boundary conditions for the quarks, a single pion, let's just think about a single pion, right? That has to have, I'm just going to write this in one dimension for simplicity, energies that are quantized in momenta. Okay, so n here is an integer, 1, 2, 3, 4, 5. Technically 0, but if I need my pion to have a finite momentum, then the smallest value of n there is 1. And so giving the quarks periodic boundary conditions give our pion, or even anti-periodic boundary conditions, give our pions periodic boundary conditions. And so we can sort of see the smallest momentum allowed for a pion, and now we want to relate that to, well, what would correspond to a physical decay process of k to 2 pi, and it gets really tricky. But what if we just give the down quark a different boundary condition? And so if you do that, the charged pion will have momenta that are actually discretized in odd integer multiples of pi over L. So instead of 2 pi n over L, where n equals 0, 1, 2, you'd get no 2 there, and n would have to equal 1, 3, 5, and so forth. So you're changing the discretization of the charged pion momenta. You're not changing the neutral pion. So if you're trying to look at, say, k plus goes to pi plus pi naught, that's not going to help us. But you could calculate an unphysical process, and this is something we love to do on the lattice, calculate unphysical processes that can be related to physical ones. And in this case, k plus going to pi plus pi plus, that's not physical because it's not conserving charge, but we can calculate that on the lattice. And we can use the Wigner-Eckert theorem to relate this to the required delta I equals 3/2 decay. So that's actually really helpful. Now, the problem with this is that you can't do the delta I equals 1/2 decay as easily. And I would encourage you to think about why that would be. Instead, you could use a different boundary condition, which I'm going to have you work out a little bit in the assignment, known as G parity boundary conditions. And G parity corresponds to charge conjugation plus, and there's a typo here, there should be an I there, plus a 180-degree rotation in isospin space about the y-axis. Okay, so IY here is just the Pauli matrix in the y direction divided by 2. And this basically, well, actually, I don't want to say what it does because I want you to work it out. But if you use these boundary conditions on all of the quarks, all of the light quarks, then this also gives the pions anti-periodic boundary conditions in the spatial direction. And you can actually use this for the delta I equals 1/2 decay process. And so, there are of course, I'm skipping over a lot of the technical difficulties. But again, I'm going to refer you to a paper by RBC and LQCD. But these combined give really good results for